Hello friends, this is Raja here. I'm an automation engineer with decades of experience in industrial control and automation. Today I'll share with you something simple. This is about the control of motors in a typical industrial context by means of a PLC. Okay, we begin by understanding what is a MCC. MCC stands for Motor Control Center. This is a common piece of electrical equipment found in nearly all, you know, significant industries. You know, this is a electrical panel that is made specially for the control of electric motors, typically three-phase induction motors. And for each motor, there is what is called a feeder. The feeder for a given motor is sized according to the power rating of that motor. If a certain motor is 10 kilowatts, the switchgear in its feeder will correspond to 10 kilowatts. And very often you will find that smaller motors are also there in the MCC, and even though each has got its own feeder, it may not be compartmentalized. Small motors do not need that compartmentalization because uh, the fault level is relatively much lower. So on the left side of the screen, you see what a typical MCC looks like, and on the bottom side, right side, you can see how the feeder looks when seen from the outside. And typically, uh, uh, the average MCC is connected to the secondary side of a distribution transformer. Okay, now within this MCC is a set of bus bars that distribute the power, and within each feeder there is this short circuit protection and overload protection for each motor. We'll look in greater detail in the coming slides. Okay, here is what lies inside a feeder. You know, this slide shows the how it looks like on the left side, and the electrical schematic is given on the right side, and how each component is depicted on the electrical schematic. On the top, we have the bus bars. The bus bars are typically called R, Y, and B according to the standard, notation for three phase, that R phase, Y phase, B phase. And immediately after the bus bar, you find the circuit breaker. This circuit breaker is for short circuit protection. Some circuit breakers also have, overload protection, but typically it can even be a what do you call a wide fuse. Of course, these things depend upon the fault level and current taken by the motor, full load current of the motor, and things like that. And then below the circuit breaker, you see there is a contactor. This is the device that actually switches on the motor. You can see there is a solenoid that pulls a set of three contacts. You know, these switch on simultaneously, and then they can feed the current to the motor. And below this contactor, you see the overload protection. This is called the overload relay. Within this overload relay, there are some bimetallic elements that get heated in proportion to the current that passes through the motor. So if it draws abnormal currents, you'll see that the bimetal element heats up and disconnects. It also gives a relay contact for controlling the external circuit. We will see all these things in the control circuit diagram. Okay, in the previous slide, we saw the power handling components of the feeder. The circuit breaker, the contactor and so forth. Here we look at the control circuit. The control circuit is the arrangement that is provided to energize the coil of the contactor. The control circuit powers the contactor. There are two commonly found arrangements. One kind of control circuit has got a auto manual selector switch, which is shown on the right side, and the more common arrangement is shown on the left hand side. This comes without a auto manual selector switch. It's a simple latching circuit. Now we look at how it works. The control supply usually 230 volt, 110 volt, AC, DC, as the case may be, and then it is also sometimes taken from an isolation transformer to reduce the fault level, and then to protect the control circuit there's a fuse, and after the fuse we come to the overload relays NC contact through which it passes, then the NC contact of the stop push button on the feeder itself, and it passes through two terminals brought out on the terminal block which are shorted. These are used if it has to be interlocked with something else. Okay, then you see the start push button, and thereafter it is connected to the coil of the contactor. The other side is grounded, and you see there are two auxiliary contacts of the contactor, one NO and one NC, which is typically the case. And you see that in the NO contact, there is a latching contact. It is connected in parallel with the start push button, and then the NO contact is also connected to the green light, green indicator lamp. It may be red in some countries. You know, they follow no convention. It's only standard practice. And then the NC contact is wired to the light that says that the motor is stopped. So also the overload relays NC contact remains closed under normal operating conditions, and when the overload relay trips, its NO is activated, and that powers that yellow color indicator lamp which shows that the motor is tripped. Okay, now let's say somebody hits the start push button, the coil gets energized. Because the coil gets energized, the supply to the contactor is sustained by means of the parallel NO contact that latches it. Now to stop the motor, of course, we de-energize the contactor by using the stop push button, which disconnects the control supply to the contactor, and the contactor opens, the contacts open, and the motor stops. Now on the right hand side, you see much the same thing, but only change here is a auto and manual selector switch. On the manuals, in the selector switch in the manual position, the control circuit works just the same. Okay, somebody presses the start push button, the contactor picks up, and the auxiliary contact latches and holds it energized. And so also the indicator lamps also are powered in a similar manner. When the contactor is on, the run lamp, green colored light, comes on, and when it is stopped, when the contactor de-energizes, the red color stop indicator comes on. And so also when there is a overload trip, the yellow lamp gets illuminated. Okay, now let us say we turn the selector switch to the auto position. Now the stop push button still has an influence because the control supply still has to flow through the stop push button, but the start push button has got no role in the automatic side. you know if somebody shorts the two terminals on the auto start terminals, then the contactor will pick up. It is this simple. Okay, I hope now you have got a fair understanding of how the control circuit works. The next task is to wire it up to the PLC so that the PLC may be in control. Now there are those commonly three signals are taken as inputs to the PLC. That is whether the motor is running or stop, whether it tripped, or if there is a selector switch, whether it is in the auto position or not. Okay, and so also the PLC's outputs have now to be connected to the control circuit so that the PLC's output may switch on the contactor off. Now, in the case of a MCC that does not have an auto manual selector switch, we will require two separate outputs. That is just like the start and stop push buttons. There will be two momentary outputs, one to start the motor and one to stop the motor. Okay, and above all, the most important thing in this exercise, the MCC's control circuit should not come into the IO circuit of the PLC. It will totally destroy the total 24-volt system, everything that is connected to it. Okay, so we have to take the responsibility of isolating it so that there's these are kept absolutely separate, and these the MCC is connected very safely to the PLC's IOs. Okay, in the last slide we discussed the need for isolating the PLC's IO voltages from the control circuit voltages to prevent damage to the IO channels of the PLC device. So for this purpose we need to use relays also. There are many kinds of relays available for the purpose, but these two commonly found kind of relays are sufficient to explain the functioning. Now on the left hand you see a double pole single throw kind of relay. This relay has got one coil and it has got a pair of NONC contacts. Actually two sets of NONC contacts. We need only one, but these things usually come with two poles. It's all right. How this works is it has got a coil which is shown as between points 13 and 14, and when the coil is energized, it will make two NO connections, that is between 9 and 5 and between 12 and 8. And in the de-energized condition, 9 will make contact with 1 as NC, and so also 12 will make contact with 4. Okay, now this is used inside the MCC or in a marshalling box, anywhere that is safe, to mount that kind of relay. And because the output of this relay, the NO contact will be connected to the 24-volt system of the PLC's IO wiring. So it is also commonly, it's a safe practice to place these relays as to receive 230-volt signals in the PLC panel itself. It depends upon the actual site conditions, the congestion and things like that. Okay, what you see on the right hand side is a 8-channel relay card. These are smaller relays. They are single pole, single throw. Means each relay has got only one NONC contact, and there are 8 channels of this, one corresponding to one channel of the thing. So you see the terminal diagram. There are it is marked by 1, 2, 3, 4, 5, 6, 7, 8 and COM. The COM is connected to the negative or ground of the 24-volt output circuit of the PLC, and the relays are driven by the PLC's output itself. Even transistor outputs can be directly connected to this kind of relay. They don't take too much current. They take typically less than 15 milliamperes or so. We'll see how this is wired in the next slide. Okay, in the last slide, we had a look at the relays that are ordinarily used in interfacing a PLC's IOs to the control circuit of a MCC feeder. Now this is more or less the typical arrangement in which uh, these are physically connected. You know, see on the left hand side of this diagram, you see the input side connections. You know, you can see the red color line is the positive interrogating voltage of 24 volt that is sent out into the field. It the first input, it comes from a pair of contacts, NO contact called CRAUT, corresponding to the relay that will pick up the position of the auto manual selector switch. And the second one, CRN, standing for control relay for run. The contact will close whenever the motor is running, and so also the third one is for detecting the tripping of the overload relay. Additionally, there are also two locally wired contacts. They are for starting the motor, that is PB start and PB stop. PB start is a NO contact and PB stop is an NC contact. Yeah, they can be NC either way. It's all handled in logic. It is not hardwired to the MCC. Okay. Now these three relay contacts are now potential free contacts. They are well isolated from the MCC's control voltage. So also on the output side, so that the PLC's outputs may safely drive the MCC's control circuit, we have got two outputs. One is called a start command and a stop command. The stop command is a NC contact of the relay that we discussed in the previous slide. Okay, how these things are actually taken in the control circuit, and we will see in the next slide. Now we proceed to see how the MCC control circuit is modified so that we can deploy our relays, the relays for input signals for the PLC, and also how the potential free contacts of the PLC's output relays are wired into the control circuit. Okay. Now consider the diagram on the left. You see there are two relays. The two sets of contacts, one for the start command and one for the stop command. You will see that the stop command is the potential free NC contact that is wired in series with the stop button. Whenever this contact opens, it will behave exactly in the same manner as the stop push button, that it will disconnect the control supply to the contactor. The contactor will drop and it will remain dropped. Okay. Likewise, the start command is a momentary NO signal. So it will momentarily close the control circuit for the contactor K and behave in the identical manner to the start push button. Okay, the mechanism is the same as before. Now, for deriving the input signals of the PLC, you see, it is common practice to wire the three relays as shown here. For example, this CROLR, that is what is detecting the overload trip signal, it is shown wired in parallel with the yellow indicating lamp. So whenever the yellow indicating lamp is tripped, it shows that the overload relay is tripped. It will correspondingly activate the CROLR relay and its potential free contacts, NO contacts, are taken into the PLC's DI. So also the run signal is driven by the NO contact of the contactor, that is named as CR run. Okay. On the right hand side diagram, these two are there. The overload relay signal and the run signal are identical. In addition, we have a third signal. The third signal is the signal that detects whether the selector switch has been moved to the automatic position. Okay, whenever it is moved, this relay will pick up. Okay, on the command side, as discussed, we need only one command. Now in this case, this is a continuous signal. As long as the start command remains closed, the potential free NO contact remains closed, the contactor will remain picked up. Okay, thus far we have understood how to correctly and safely do the interface wiring of the PLC's I/O with the control circuit inside the MCC feeder. Okay, now it is time to look at how to write the logic. Now, because this is simpler, I look at the case with of the feeder where there's auto manual selector switch available. Okay, we examine how the logic works in the first run. The first one, the signal from left to right is the automatic permit. That is it shows that the selector switch has been selected there, and then it is followed by three sets of contacts in parallel. That is the start push button, and then followed by the timer's output. That is a timer at the end of this run. Whenever this command pump start stop, that is CMD PM pump underscore SS, that is a single command, because this when there is a auto manual selector switch, you need only one output. Okay, it's a continuous signal. All right, and then the third one in parallel is the start command along with the run feedback. Okay, then you have a series of NC contacts, which are the stopping conditions. Okay, now they are like lockout, tagout locked, then fail to start, fail to stop, the overload trip, which is a physical signal. That is, we have discussed how that relays wired, that CROLR, and trip didn't run, which is a derived signal in the second run, and then the wired push button stop, which was a NC. That is why we are using a NO contact here. Okay, and finally you have the output enable coil, which is the command pump underscore SS for start stop. Okay, how this works is, assuming all these conditions are true, that is there is no lockout tag out, there is no failure to start, no failure to stop, no overload trip, no trip didn't run, and the stop push button has not been pushed, then when somebody pushes the stop button, the power will flow left to right along the logic and energize this output CMD pump SS, that is start stop, and so also it will activate this pulse timer for just 3 seconds. Okay, so the first parallel contact is the output of this timer, so it will remain latched for at least 3 seconds. If within 3 seconds you get the run feedback, then the run will remain latched, and the run command can be sustained. If, however, even after the lapse of these 3 seconds, you don't get the run feedback, then the command pump SS, that signal will fail. It will turn off, and the contactor will drop inside the feeder panel. All right. Now, why this delay is because the run feedback is never necessarily due to the contactor picking up inside a feeder. Often, because if someone expects a pump to not be primed, then there is a flow switch in the line. Not only has the pump to start up, but there has to be a flow of water in the line, and that will activate the flow switch. And that output of the flow switch is taken as the run feedback. So this timer is to take care of such delays. Okay, and the time delay is set accordingly. See, if you want a mere run feedback, even 20 milliseconds is sufficient, 50 milliseconds is sufficient for the contactors run feedback to come. Of course, larger contactors require a little more time, but still in the millisecond range, 100 millisecond and all. Nobody does like that. People usually use 500 millisecond, 1 second like that. When there is a directly uh, wired run feedback from the contactor itself. Okay. So any one of these conditions coming, that is the overload relay trips or the stop push button is asserted, will cause this rung to go false, and of course the contactor will be turned off. The second rung is about getting a tripped in run signal. Why is the signal required? It may be on account of the overload trip itself, or due to some other mechanical issue, due to a burst of the pipeline, a belt failure or anything like that. Because as I told you, that run feedback is not necessarily from the contactor. It can be any other signal derived to say that the machinery is in motion. Okay, a pump is pumping water, or a gearbox that is driven by a system of belt and pulley. The belt is not broken; it is moving. Okay, if the belt breaks, you will lose the run feedback. Okay, so this is for detecting these things. So how this run works is like this. At the first onset of the run feedback, we latch the once run uh, signal, means it has been run at least once. It has started running, and any subsequent vanishing or failure of the run feedback signal will cause that once run to be set, and then this in the absence of the run feedback, the tripped in run flag will be turned true. Okay, now you take a closer look at the two sets of parallel contacts after the the first set of parallel contact, that is the tripped in run NC contact parallel with the reset feeder. What this means is, if it is in a tripped in run condition, then the reset feeder signal that is coming from SCADA has to be asserted so as to clear the tripped in run. So also the PB stop in parallel with the tripped in run means when there is no tripped in run signal, in the normal course, in case of normal operations, the normal operation with the stop command, stop push button input, will reset this signal so that it doesn't unnecessarily raise an alarm. Now, why this is arranged like this? It is because of the De Morgan's theorem. You look at it and think over it. I mean, you uh, oh, post your explanation in the comment section. Okay, it will be an interesting exercise. The same philosophy is used for the fail to start and fail to stop flags. Now these three derived flags must not allow the motor to be started again without asserting the feeder reset input. Now we look at the case when there is no auto manual selector switch available on the feeder. I mean, such a signal has to come from the HMI or SCADA. Okay. And in addition, there is one important difference. That is, instead of one continuous signal, you require two momentary start and stop commands. See, this is a very simple thing. The command pump SS earlier was a output signal. Now we get here as a memory signal, which is continuous in nature. Now the next rung, it shows on the rising edge. We have put a pulse timer for 500 milliseconds, and so the output start command will switch on the start command relay for a mere half a second. That is sufficient, because if you look at the previous diagrams, how the control circuit is arranged in such a kind of feeder, this is exactly in parallel with the start push button. Okay, this is sufficient. It's just like somebody pushing the start button for half a second and removing his finger. It works in the same manner. The third rung shows the identical mechanism. When this pump has to be turned off, any one of these conditions uh, has to be asserted. For example, let us say the PD stop is pushed, and so this continuous command fails, and on its falling edge, likewise we take a half second pulse timer, and that gives a which opens the NC contact with the stop command for half a second. That is sufficient to stop the thing. Okay. The rest of the discussion about deriving the tripped in run and the fail to start and all are common in both cases. Okay. Now we discuss two other alarm signals. That is the failure to start and failure to stop. These two are very simple. Now this is a means of the first rung. You see failure to start. We take the falling edge of the timer's output. That is the pulse timer has got an output, that is a wait for fb.q, which is another way of saying that the waiting period has elapsed. If by the time it doesn't detect the run feedback and the reset feeder is not asserted, then the fail to start signal will be latched. All right. Of course, the fail to start signal has to be reset before the next start by means of the reset feeder signal. Okay, now this is a very simple arrangement. Okay, now we take a look at the failure to stop uh, alarm flag. Now this is very similar to the way we got the tripped in run condition. Now this can happen due to many things. Why failure to stop? It is not always required, but there are some instances. There it is possible that a thing has not stopped running. There are things like centrifuges and things like that. Many conveyors which are having heavy loads on an incline and other things. They have got a system of brakes. What happens is when the motor stops, automatically the brakes also have to engage. In case of material handling equipment and all. But sometimes if the brake shoes or something gets worn out or due to other, inertial factors or due to load, it is possible that the de-energized motor may start running by itself. And we are detecting motion, mind you. It's not merely the contactor, going off. We are arranging the run feedback in a manner to detect movement of machinery or the flow of water in pipe and things like that. Okay. Now let us say we have withdrawn the start command. Okay. And you are detecting a falling edge. and that is latched as no command. Okay, now within a period of 5 seconds, as in this case, we should have the run feedback. Else, if we still have the run feedback, means we have to flag it as fail to stop. It has to be latched. Okay, so this is, as I told you, similar to the you know the tripped and run condition. When you withdraw the command and wait for a short while, then the run feedback has to vanish. Otherwise, this has to detect that fail to stop flag. Okay. So in the normal course, whenever the run feedback comes in, when the run feedback vanishes by itself, this alarm will be reset. In case the run feedback comes, it will remain on. And then, because even though there is a timer, the left side of the timer will remain true. And until the time this is reset, the fail to stop flag will continue to up. Again, this just by the De Morgan's theorem, these two sets of parallel contacts, that is when you have the flag fail to stop, it can be cleared only by that reset feeder uh, command from SCADA. And when there is no failure to run, this no command can be unlatched by the run feedback, the absence of the run feedback itself. Okay, it's fairly simple. But as I told you, in the case of the stopped and run, please think of it along the De Morgan's theorem, and you will get a notion of how this has been arranged. Okay, it works. I have seen that. Now, having correctly configured logic and ensured that you got the common alarm signals, you have one more signal you have to arrange. That is, you have to inhibit uh, starting of the feeder motor for safety, and this is necessary from SCADA also for logging. You see, in certain large plants, there are large vessels with agitators inside and all. Sometimes, for maintenance purposes, people are sent inside the vessel with agitator and all. So when personnel are working inside the vessel like a blender or a reactor, nobody should start on the machine. People will get killed. So for these purposes, there is a lockout, tagout done. This is formally done from SCADA. I mean, you have to lock a particular motor feeder by means of password, and it will also be logged. So such and such person logged out a certain motor at such and such time, and this was cleared at a such and such time. You know, so this is done for the purpose of safe maintenance. You know, in plants and all now, all these things have become routine. Safety is very important. To disable the thing, and such signals are necessary for logging in SCADA, so that from these signals it is possible to find out also how long it was taken out of service, it was put in lock mode for the sake of maintenance, cleaning and all that. See, it's actually very simple. There is a that signal called lock. There's a lock motor input. It's a soft signal from HMI SCADA, and this can be done only when it is not running. There is no run feedback. Okay, this can be deployed only when the equipment is not in use. Okay, when it is locked, it will stay locked. And if you look at the motor logic, this LOTO lock signal will prevent the command from being energized. Okay, of course, in the rung here, it looks very simple. But that lock motor and clear lock are originating in SCADA, and though these are discrete signals, they are put in place after properly, entering the system by way of authority authentication. And after these things are done, it is recorded with proper timestamp and who did it, who locked it, and who cleared the lock and all that. Okay, but yes, it's a simple principle, but it's very important for the purpose of safety. This is also a commonly found feature, and most customers will appreciate you providing such features in your PLC system. So that's about it for this thing. One final thing. When you have a large number of motors, the logic that we have deployed, we are in so far, can be encapsulated by means of a function block. Means you have a function block and all these signals are there, like auto mode, run feedback, overload, start push button, stop push button, lockout, clear lock, reset fails. All these are the inputs and you have the corresponding outputs. So once you make a function block like this, you may have 100 motors, 300 motors in a plant. The same function block can be deployed again and again by tying out. Of course, that is another thing. It's common practice these days. Nobody does copy and paste and things like that. Okay, okay. Now this channel I have started with a view to discuss the philosophy of control. That is why it is called a control philosopher. The ways of arranging logic by understanding how things work. What is needed towards safety and how industrial logic is developed to at least meet a minimum decent standard. Now, there are many ways of doing things, but this is a guidance. This is not a it's some guidance. It is a guidance to the philosophy of control, not how to program PLCs or how to make things. For a particular brand of PLC, I'll be discussing many topics about this control philosophy. Is how to develop control strategies, how to implement controls, in the logic. Okay, I see there are not many guidance, not much guidance available on the internet. Here and there you see something in a specific context, but no. So I thought I might add value and be of help to somebody. Thank you for looking in my channel. If you have any questions, if there are any topics you'd like to me to make a video about, I'll appreciate that. Please leave your comments in the comment section. Thank you. This is Rajesh Iyer signing off. Thank you. Bye.